We have so far spent a lot of time thinking about what happens with the infinitely small. In the case of the slope of the tangent line, we look at the difference between 2 points and we make those points infinitely close together. Our start off with the delta x of a secant line becomes the dx of our tangent line. We also looked at this in the case of integration when we built an integral. We wanted to do length times width, and we made the widths the delta x, and then just let the delta x become infinitely small. We made our width infinitely thin. So we did a thing more often over a smaller interval. We did a thing more often over a smaller interval. So our delta x's always became dx. The dx in the definite integral is the delta x that we had for the width, and the f of x was the length. The d over dx is the derivative of the top, the rate of change, or the change in the top, the delta y, divided by the delta x, when the delta x becomes infinitely small. There's another kind of infinity that we need to study in single variable calculus, and I would like to preview that today as we close out part 1 of single variable calculus, and we all get ready for part 2 of single variable calculus. The other kind of infinity that we're going to be concerned with infinitely long. The other infinity that we're going to concern ourselves with is a discrete infinite sum. So a sum with an infinite number of terms. So here's another kind of infinity that we need to be concerned with. A sum with an infinite number of terms. The question that we're going to be asking when we look at this sum with its infinite number of terms. Oh, first of all, let's notice how different this is from our infinite number of terms in an integration. In an integration, we had an infinite number of terms. We had an infinite number of rectangles crammed into a finite space, the interval from A to B. So that's the difference between this and the infinite sum that we had in an integral. We had a definite integral from A to B of f of x dx. That f of x dx represents the area of a rectangle, an infinite number of rectangles crammed into a finite interval from A to B. Here we're talking about something else. Rather than trying to cram a bunch of rectangles, an infinite number of rectangles into a finite space to represent some continuous change in our height, we just have a discrete infinite sum, a0 plus a1 plus a2 plus a3. We can tell that we're going to have an infinite number of terms because I put dot, dot, dot at the end. And also, we're not going to worry about making a continuous sum because I put plus signs everywhere. So rather than having to change my sum into a definite integral, because I'm trying to model a continuous change, I got steps. I can label them 0, 1, 2, 3, 4, and so on. We can label all this stuff. So this gives us a different kind of infinity. I just said different kind of infinity. So this kind of infinity, we would classify as what we call a countable infinity. This is a very clever name for this kind of infinity because it is countable. We can label each individual thing. The fact that I could just stand here and throw this out there is very controversial when we first started thinking about these things, because it leads to some very weird results. So this symbol here is actually just an N. It's an N where you separate the bottom part and the top part, and you make that double in the middle. So it's a double N. A double capital N. That's the symbol that we use for the natural numbers. Natural numbers are just the ones that we use to count stuff. I always forget whether we include 0 in the natural numbers. And it's like the whole numbers and the natural numbers. It's not really that critical. You can check me in the comments, except for the fact that I disable comments on YouTube. So, So, go ahead and add me about that. Maybe 0 is not in there. But the natural numbers, 1, 2, 3, 4, natural. Above this, we have the integers. This is where we include the negatives. We include the opposites of our natural numbers. We put those together. This is going to be the integers. The letter we use to represent the integers is, of course, the letter Z. That's the only thing that makes sense. So for integers, we use a double Z, because obviously we use a double Z. I honestly don't know. I don't know. Nah, that would make kind of sense. But from like an English perspective, maybe integers is a different word in some other language. And they're like, oh, no, we got here first. Maybe it's just that we're adding stuff to the natural number. So we just took the N and turned it sideways. Honestly, I don't even know. You could tell me that if you told me with enough certainty, it's just because it's like an I, but we like italicized it so it makes it look like a Z. If you told me that with a lot of certainty, I'd be like, all right, that's fine. That's just as good as any other explanation. But that's a double Z. A double capital Z specifically. Then we have another set of numbers called the rational numbers. The rational numbers are just all the ratios of integers. The rational numbers are all the ratios of integers. Fractions. I suppose we should specify that P and Q don't have any common factors, and we can simplify stuff, but 6/3 is just 2. So that's not a whole separate thing. But we're just saying it's everything that looks like P over Q, where P and Q are integers. Since Q could be equal to 1, that means that not yet. Since Q could be 1, that means all integers are also rational numbers, just like all natural numbers are also integers. And so all natural numbers are also rational numbers. Note that Q can't be 0 because that would mean P over Q is not defined. And so we would not be able to put that in the set. We have an abbreviation for the rational numbers as well. And it is once again super obvious. We would obviously use Q to represent the rational numbers. It's been Q for a lot longer than QAnon has been a conspiracy theory. So it is exceptionally hilarious that the irrational conspiracy theory is summarized with the symbol for rational numbers. Yeah, that's the funny part, I guess. But also the terrifying part. This is what happens when you take bad information like the earth is flat and just let people run with it. Anyway, we use a double Q because Q obviously for rational numbers. Mainly this is because, at least this one we know because R is spoken for. R is our abbreviation for the real numbers. This is our rational numbers plus the irrational numbers. And this is our first continuous set. And this is a double R. Double R. That's the symbol for the real numbers. We write a double R because we found ourselves writing all real numbers way too often. Right? How do you write that? You just make an R and then put an extra vertical on it. Sitting above the real numbers, we have the set of complex numbers. Which is a set of everything that says A plus BI, where A and B are real, and I is the square roots of -1. At least this one makes more sense. We use a double C. And these are all subsets of each other. The natural numbers are a subset of the integers, which are a subset of the rational numbers, which are a subset of the real numbers, which are a subset of the complex numbers. So if we start off with the natural numbers in this little box. I'm not good at drawing the double N. That's a subset of the integers. Which is a subset of rational numbers. Which is a subset of real numbers. Yeah, complex. which is a subset of the complex numbers. A subset of our real numbers are all the rational numbers plus the irrational numbers. So the irrational numbers show up in this real number set separate from these other ones. So there's our irrational numbers sitting as a subset of our real numbers. That is entirely separate from the rational number. Irrational numbers are real numbers. It's part of it's a subset of the real numbers that is separate from the rational numbers. In the complex number set, we've got all those real numbers, but we've got all the pure imaginary numbers. So over there, we'll have imaginary numbers, things with a factor of I in them. So that will be a subset of our complex numbers. But the naturals are a subset of the integers, are a subset of the rationals, are a subset of the reals, are a subset of the complex. We just keep adding stuff. We start with our natural numbers. We add the opposites to get the integers. We add all the ratios to get the rationals. We add the irrationals to get the real numbers. That's where we start having a continuum. We add the imaginary parts to get the complex numbers. Here's one of the reasons that infinity is weird. We have some experience with this infinite business because we are calculus students. About to move on to phase 2 of calculus expertise. We understand, or we think we understand, the concept of infinity. Hopefully, after being through your first calculus class, you recognize that whatever understanding of infinity you had before was lacking. So at this point, you should feel like you understand less about infinity. This is the nature of education. When you graduate, you should have more questions than when you matriculate. When you're finished with college, you're supposed to have more questions than when you started. When you started calculus, you might have been confident in your understanding of the concept of infinity. Hopefully here at the end of your first class, where infinity is taken seriously, you have more questions about infinity than you did at the start. Infinity is the concept of infinity. Yeah, we try to think of it as a number. In this class, hopefully we learned that infinity is most definitely not a number. Notice that infinity is not included in any one of these sets. It's not a number. So when you're arguing with your siblings and you're like, oh, nah, infinity, then it's over. When they go, yaha, infinity plus 1, it's like, oh, got you. Infinity plus 1 is the same as infinity. You ignorant wretch. I don't know how siblings fight. I'm an only child, so you call each other ignorant wretches, right? Is that how it works? If not, it's going to be now. You vile, ignorant wretch. Your lack of understanding I find disturbing and disgusting. Get thee from my sight. So. Incidentally, that's also a good defense when you're walking around the city and you don't want people to talk to you. Just talk like that to yourself, and then people will be really well. My wife is usually not happy when I do that. I'm just kidding. All right, here's a weird thing about infinity. See all these natural numbers? And see all these integers? See how we take the integers and the natural numbers is a proper subset of the integers. These two sets, same size. One is clearly a proper subset of the other one. But in cardinality of these sets, if we look at the number of things in each set, yeah, they're both infinity, but those sets are the same size. See this set here with the rational numbers? All the fractions now, not just denominator 1, like in the integers, denominators of all the other integers. These two sets, the integers and the rational numbers, same size. Same size. If we have to make a match between every integer, or actually even better, every natural number and every rational number, they all match up because the sets are the same size. This set here, the real numbers, that one's bigger. That is a bigger infinity than the rational numbers. Natural numbers, the integers, the rational numbers, those sets, although they're all infinity, they're the same size. This real number, that one's bigger. This is really weird. We know that the sets are the same size, because if you could make a one-to-one on-to correspondence between two sets, then those sets must be the same size. They must have the same number of elements. And the fact is, if you can make a list of all the rational numbers, then you have a countable infinity, and it's the same size as the natural numbers. And the thing is, we can make a list of all rational numbers. We've got 0, and then we've got 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, and so on. Then my next row, I'm just going to make the denominator 2. 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, and so on. Then in the next row, I'm just going to make the denominator 3. The very fact that we can list all the rational numbers means we're dealing with a countable set. Now we're doubling up a lot here. We're doubling up a lot here, so we should get rid of any copies. Anything that is equal that we've already listed, we can get rid of it. So like 2 over 2 is 1. So we can get rid of that because it's just a copy. That's just equal to 1. 4 over 2 is equal to 2. So we can get rid of that. That's just a copy of the 2. 3 over 3 is also just 1. So we can get rid of that. 4 over 4 is also just 1. We can get rid of that. 2 over 4 is a half. So we can get rid of that. But what we've got is a list of all the rational numbers. Now, this is all the positive rational numbers. So if we want to be complete, we could put the negative ones on the other side. Now we show a set is countable by just counting things. So here's our correspondence. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I can count the things. The typical way is kind of like go up and down like this, kind of sweep back and forth on diagonals. But the mere fact that we are listing them means we have a countable set. And every rational number gets paired with a natural number. So the sets are the same size. I'm being a little bit casual by saying that the sets are the same size. I'm saying that the cardinality of each sets is the same. Any questions? Math controversies are very weird. Because when Cantor is like, oh, check it out, same kind of infinity. And they're like, oh, well, that's just because it's infinity. And then we're like, oh, no, the real numbers can't make a list. It's not possible to make a list of real numbers. Because as soon as you claim to have a list of real numbers, we just make a number that's not on your list. When you include that number on your list of real numbers, we just make another number that is not on your list. Any questions? There's a difference between our two kinds of infinity. There's the infinity that's countable, the natural numbers. And then there's our uncountable infinity, the real numbers. One of them is like a discrete infinity, where we can separate things out with a plus sign. If you can separate things out with a plus sign, that's a countable infinity. If you've got to integrate because you're smashing things together into a continuum, now you're dealing with an uncountable infinity. So once again, there's our difference between a discrete set and a continuous set. Another interesting fact about these infinitely large sets is that the real numbers are, that's an infinite set. The rational numbers also an infinite set. The real numbers are a bigger infinity. So that raises the question, how much bigger? It is in fact infinitely bigger. Because the probability of choosing, when you choose a rational number, the probability of choosing a rational number randomly from the set of real numbers is equal to 0. If you take a dart, toss it at the real number line, and the dart will land on one real number. That is, you pick a real number at random. The probability that that number is rational is 0. That's how many more irrational numbers there are than rational numbers, even though the rational numbers are an infinite set. Even though between any two real numbers, there's an infinite number of rational numbers. And in between any two rational numbers, there's an infinite number of real numbers. That's crazy. This is why you have some really skewed views about how things work. Think back to algebra. Remember learning to factor polynomials? Remember we're learning to factor polynomials? Find factors of c whose sum is b, like x squared plus 7x plus 12. Factors of 12 and make 7, right? 3 times 4. and you just practice the crap out of just factoring polynomials, then you get this skewed idea. Most polynomials are factorable, which is not true at all. Most polynomials are not factorable. The reason that you encounter more factorable polynomials is because we want you to practice factoring. So we've built in this belief. We've built in a system where you might believe that most polynomials are factorable because most of the polynomials I've seen are factorable. Like on a quiz, when you're factoring polynomials, maybe one of them is prime, right? And I was like, oh, we got to remember that not factorable is a possible answer. But if I just dumped 10 polynomials at random on a piece of paper, they'd all be prime. If we pick them truly at random, even with integer coefficients. That's crazy. Questions? How's everybody okay? But actually, the way I've drawn it here is not really representative because the real number should be infinitely bigger than the rational numbers. But I don't have a finite, I want to cram it all into finite space. So I guess it gets more dense on this row right here. What's that? No, it's the same size. Yeah. The complex numbers, same as the real numbers. These two are the same, bigger, same, infinitely bigger than these three. Infinity is weird, and there's a lot of controversy when we start thinking about these ideas. What's that? What's included in the real number? Oh, yes. But really, all we're doing with a complex number is just two real numbers. Right? A complex number is just two real numbers smashed together. Thought of as one number. We don't really get anything in terms of size. Any questions? So that's the other kind of infinity that we have to concern ourselves with. We won't get to learn about this until next semester when we get into sequences, series, and power series. But we're going to be looking at, we want to be looking at a sum with an infinite number of terms. So rather than taking an infinite number of, say, areas and smashing them down into a finite interval and making a sum that way in our definite integrals, we're just having them all the same space, evenly spaced apart. We're looking at a countable infinity of terms and seeing what that will produce. Any questions? Comments? How's everybody okay? The other thing I want you to think about is think about how early you are, how early it is in your mathematical career. I know you think this is very late in your mathematical career, and it might be. Maybe the next class, Calc 2, is the last math class that you take. For most of you, Calc 2, then maybe linear algebra and differential equations. You might have 3 math classes to go. But I want you to think about your position after you take those 3 math classes. What percentile do you think you're going to be in terms of mathematical knowledge at the end of your math classes? Even stopping with Calc 2. What percentile are you in? It'd be somewhere in the 90s, conservatively, just of mathematical knowledge, walking around. And that's, and I'm telling you that this is the beginning of math. one of the things that I tell you a lot this semester, and I'm gonna tell you a lot next semester, is that you haven't started your math classes yet. All this stuff is just pre-math. People ask what comes after calculus? Math. Math comes after calculus. This is all preparation to receive those ideas. And that's still putting you in the high 90s as far as percentiles go.
So who is
The top 1%? I don't know, people that normal people can't have conversations with because they just know too much. Which raises another interesting question. We talked about this a lot when we were in graduate school. When we realized, this is when we were graduate students in math, and we realized that we were the only people that we could talk about our work with. So I can't talk about to my friends about other things. About these things, these work things. You know what I mean? So anyway. And I haven't been that far. I only have a master's degree. Anyway, that's what's coming up next. I just want to give you a preview of the other kind of infinity. The kind of infinity that we've dealt with so far is the infinitely small, taking an infinite number of rectangles and cramming them into a finite space to produce that continuously variable curve, that continuously variable length times width. Now we're going to let them separate with these plus signs, and we're going to think about what we can get out of these infinitely long sums. What can these infinitely long sums tell us about numbers and the things that we want to know about? Any questions? Comments? Deep thoughts? Meetings from here to the end of the semester. That's Thursday, Friday, and then all of next week will just be on Zoom. I'm going to be sitting up in my office. I'm going to open up Zoom. If you have questions, you can jump onto the Zoom for that part of the meeting. If you don't have questions, then these meetings are optional. So I'm not going to be coming to this room to run the meetings starting tomorrow. So all classes are Zoom. I'm just going to be sitting in my office. I'll open up Zoom. If it's not open at 1 o'clock, then I usually don't start, or 12 o'clock. I usually don't get my stuff together until 12:10 anyway. Send me an email and I'll be on shortly. But only if you have questions. So if you don't have questions, feel free to just go get lunch. And while you're having lunch, just sit there and think, I am not doing calculus. Nice. All right, that's going to do it for the meetings for this week. I will see you all possibly on Zoom and possibly next semester in Calc 2, if you're so unfortunate to be in my class. Bye. Everybody, thanks for playing the Calculus 1 game with me. I'll see you all next semester.